Hi everyone, welcome back to another Oxbridge and Imperial engineering, sciences, natural sciences, physics and mathematics interview problem practice study session. Today we'll go through this problem step by step. I haven't seen this problem before. I'm sure you haven't too. So let's dive right into it. This is called the gold bar problem. So once upon a time, a king asked one of his servants to make 18 genuine gold bars, each weighing 100 grams. The servant then made 17 bars as requested and one bar using only 99 grams of gold. Unfortunately, this fact quickly spread around the palace, and the king realized that one of the bars would be lighter than the others. Given that he possessed an extremely accurate balance scale, what would have been the minimum number of measurements he had to make in order to distinguish the lighter bar? So we know that the expected weight is 1800 grams, and the servant has made the actual weight is going to be 1700 plus 99 grams of gold, which is 1799 grams. So the servant has made 17 bars as requested, one bar using only 99 grams of gold. So the question asks, what is the minimum number of measurements he had to make in order to distinguish the lighter bar? Well, essentially, if you're using a balance, you'd have to put on one of the balance, one side of the balance with the actual gold, and the other side with the one with the defect, and the defect one would move upwards because it weighs less. So what he could have done was, so here's balance, right? What he could have done was separate the 18 gold bars into 9 each and weigh them up. And because there is a presence of a defect, what he would see is one of the sides would go down. And so the side that's been up is lighter than the side that's been down. So therefore, out of the 9 gold bars, there's going to be one gold bar that is 99 grams. So this is the first test. So the second test would be to essentially put in 5 of the gold nuggets, 5 of the gold bars in one side, and the other side with 4 of the gold bars from the same side plus 1 of the gold bar from the other side, because we know that that one will always be 100 grams. And again, if there is and we know that there is definitely going to be a side that contains defect. And if the defect is in this side, then we can proceed to third test. So we know that it's going to be one of the 4 bars that contains the defect. So you put in 2 each, and there will be another defect. So then the fourth test is you test one of the 2 that has the defect. The defect one would be lighter, therefore move up the balanced. So therefore, I think the minimum number of measurements he had to make was 4 measurements, and 4 measurements would be sufficient in order to determine if he had a defect or not. And let's just check. Oh no, it's not 4. It's not 4 measurements. So there should be an even easier way to answer this question. Okay, so if it's not 4, then what we can say is, okay, so going back to this example here, so when he had 9 bars on this side, and he knew that one of those bars is a defect, what he could have done was randomly choose one of the 9 bars out and just place it somewhere else, right? And then have the rest 8 of them have 4 on either side and weigh them. And if the 4 are equal to each other, right, then that means the one gold bar that has been taken out is the defect. And if it's not equal to each other, we can continue to have 2 and 2. So therefore, the minimum value would be, okay, not 2. Okay, so what is the idea here? Okay. Okay, so it's not 4 and it's not 2. Let's reread this question again. It's given that he possessed an extremely accurate balance scale. What would have been the minimum number of measurements he had to make in order to distinguish the lighter bar? So, essentially, this scenario is you have a balance, you have 18 of the bars. How many measurements will it take to, hopefully figure out which one out of the 18 bars are defective, which means they are lighter? Not sure. Okay, so my first instinct would be to divide the 18 into 2 sets of 9 and weigh them. And after this test, you'd figure out where the 9 would be, right? So after one test, we are able to figure out which we're able to reduce the number of possibilities, number of gold bars, down to 9. So instead of choosing 1 from 18, now we're choosing 1 from 9. So now the problem is, if we have 9 of the gold bars, how are we supposed to figure out which one, where the are we able to determine exactly where that gold bar is? How can we distinguish it? Because the only distinguishing factor is that the defective gold bar has 99 grams, whereas the non-defective or ordinary standard gold bar is 100 grams. My second method of going about this is to divide that 9. So let's divide that into 3 sets of 3. So 3 sets of 3. So if there is is 3 sets of 3 good, or 2 sets of 4 and a 1? You see, I'm not sure. So we've done the first test. This is the second test. So if you do 3 sets of 3, there are 2 possibilities. One of the possibilities is that the two sets of 3 has the same weight, and this means that the defective piece is in the other set of 3. And alternatively, if under this circumstance there is an imbalance on the balance, what would happen is we would say that the defective piece is in 3. So so just so like regardless of what combination it is, you'd eventually get to test 3. So you have 2 of the gold bars hanging and 1 of the gold bar apart. So by test 3, you're able to figure out which one is defective, because there are only 2 scenarios here. First scenario is when the 2 gold bars you selected are equal in weight to each other, in which case that means that the defective gold bar is the one that's been omitted out. Conversely, if the balance is imbalanced, that means the defective piece would be the one that flips up on the balance because it's lighter. So therefore, in 3 tests, you're able to determine which piece of the bar is defective. So it's 3 tests.